All right. Number 12. The graph, I believe, is that the one that was 1 over x? So it kind of comes down like so. And then you got the line x equals 1, which would be about here. You got the line x equals 2, which would be about here. And so it's this region right here. Now, the thing that you may or may not have seen, now you were supposed to, I think I was fairly clear on this yesterday, you were supposed to do what on these? The shell method. The problem said you would revolve around the x-axis. Now, I haven't decided for sure how it will be on the quiz. I want to make sure you can do both the disc washer method and the shell method. Remember, those are alternatives for doing volumes of revolution. Those are different than the solids on a base. Solids on a base, there's just the one way to do it with the slicing, as we were doing before. But the shell method that we learned, for those of you that were not here yesterday, and hopefully you've had a chance or probably should take the opportunity to watch the video from yesterday. The shell method is a alternate form of disc washer. All right? So this would be one where you would choose, if you had the choice, to do a disc. Because you'd put a vertical strip right there, it would sit right on there, and it would rotate, and it'd be a really nice, easy problem with a disc. But I told you to do shell. Shell's not going to be as nice a one. So if you had the option to pick, you wouldn't have picked shell here. So if I want you to be able to do both, on the quiz I might make some of the problems a lot easier with disc, some of the problems a lot easier with shell, and therefore you would probably choose at some point in time to do both methods. But I also may just tell you, like this problem, you have to do it a certain way in the directions. So you just have to read the directions. If I don't tell you a method to use, if it just says find the volume, then you're free to use whatever. Okay? So on this one, we have to do horizontal. What makes this one harder to do horizontal? You have to split it into two parts, because right there, remember, now, again, one of the key things to remember, and again, for those of you that are gone, a little bit of a tip, if you've got a horizontal axis of revolution, when you're slicing it, you would have perpendicular and vertical strips. The shell method allows us to take a horizontal axis of revolution and do horizontal strips, because it's wrapping around the axis instead of slicing through the axis. So if you've got this, okay, a vertical axis of revolution, the shell method is going to be vertical strips. The slicing will be here, horizontal. So in this particular problem, since we have a horizontal axis of revolution, the shell method is going to be horizontal strips. Well, down here your strip is going to touch those curves. Up here your strip is going to touch those, two different things. So this was y equals 1 over x. We also need to know that when we have horizontal strips, we solve for x. Well, it turns out it's the same basic equation if you solve for x. X equals 1 over y. So the first, we have to, should write this down. We've got to find P and we've got to find H. Well, how do we do H? It's just the length of the strip. So it's the same old thing we've always been doing for H. So this top strip here would be this x coordinate, which is 1 over y, and minus this x coordinate, which is 0. For the other equation, the bottom half, the height of the strip is just going to be this x coordinate 2 minus this x coordinate, which is 1. So very simple like that. What's that? Oh, yeah, I'm sorry. It's this x coordinate minus this x coordinate. This x coordinate is 1. Thank you. Yes. Okay. P, then what did we say P was? From the center to the strip. Here's the center. Here's the strip. We said we would just label that strip with a Y when it's horizontal. When it's vertical, we label it with an X. Because this strip has some Y position since it's horizontal. The entire strip has a Y location. Maybe here, this is 1 up here, so maybe this is 0.8. How far is it from the center? It's 0.8. It's Y minus 0. So that's where we do the top minus bottom. This strip would also be labeled with a Y, right? But this strip is down here lower. It's not as far from the center. That's because its Y position is littler. It's got a littler Y value. So we just label those strips. So the P is going to be Y minus 0 in both of these. And that's not a problem. That's fine, okay? Because y is going to be littler in that one, and y is going to be bigger in this one. So p will be bigger in one than the other, but that's what it is. So the formula was 2 pi, then p, and then times h. And so for the first part, and then, well, that's actually the top half. And so this is the point, what, 2, 1/2? So these strips are going to go from 1/2 all the way up here to 1. And then the other integral is your 2 pi, p is y, times h, which is 1, dy, and then those strips are going to go from 0 up here to 1/2. Okay, and there is the setup for number 12. Okay, you said 17? What was the function on 17? Square root of x. Okay, so we had a graph, something like this. Y equals square root of x. Where are we revolving around? X equals 6, which is out here. And what was this, 4? So right here's the point 4, 2. We're revolving around this. So what type of strip do we need? We need a vertical strip. Let's put that in red. So we got a vertical strip right here. When you've got a vertical axis of revolution and you're doing the shell method, you're going to have a vertical strip wrapping around as opposed to slicing. All right, so we're going to have a vertical strip. That would be a good reason to have that choice. So your h is going to be the height of the strip, so it'd be that y value, square root of x, minus the bottom y value, 0. And p, we just label that x right there because it's got an x position wherever it's located, and how far is that from the center? 6 minus x. P, for those of you that were gone, P is always like that. It's always 6 minus x minus 0, x minus 1, 2 minus y, 3 minus y, y minus 7, whatever. It's always going to be that kind of thing. This distance, if this strip was at 2, how far is it from the center? It's 4 away, 6 minus 2. So 6 minus x. So we set up our integral. It's 2 pi times p times h. And the strips fill the space from 0 to 4. So there's 7. Okay? Now, if you had a choice, what would have been the other way you could have done this one? Horizontal strips. Would it have been a disc or a washer? You'd have had empty space, right? Here would have been your outer radius. Here would have been your inner radius. You'd have had big R equals right minus left. So that now we need an x, so we'd have to solve this. So we'd have x equals y squared. So we'd have this x, which is 6, minus the left x, which is the y squared. Your little r would have been 6 minus 4. And then our integral would have been pi big R squared minus little r squared, and it would have went from 0 to 2. Strips fill the space from 0 to 2. That would be one that I would say is equally difficult or equally easy, however you want to look at it. Either way. So on the quiz, if I said you had your choice, I could see a lot of times I have people work it both ways. I would suggest to you on the homework, even when it says you have to do it by shell, do it both ways for practice. Okay? You type that in. That should be a dy, by the way, down there. Sorry. But you type this in, those two better come out the same. All right? And I think for extra practice, 22, because the answers are here. I'm here at 7 in the morning. The book is here. You can come see how you're doing. Now, maybe you want to wait until next week, closer to the quiz, and you want to do that, or over the weekend might be not a bad time to go back because you know the quiz is coming, and we got these things to be working on. Like 22, you did 21, 22 would be a perfectly good one to do. Number 20 would be a perfectly good one to do. Number 18 is a good one. Number 15 is a good one. You know, most of these, 13 is a really good one with the shell. 10 and 11 are good ones, right? So though on that packet, we've only picked out a handful of them here, but there's certainly other ones to do, and that's probably something you're going to need to do before the next quiz, is to come back into this LH packet and redo ones that you had already done, and just pretend you hadn't seen them, because let's face it, the reason you review them is you might have forgot already, right? So it's not that big a deal. Or pick some other ones. I think that's going to be important for you to do. All right? But we do have a couple more things to do. And that's another reason I'm talking about reviewing these things, because, you know, more things we add into it, the tougher it is to remember all the different things. So that's important. All right, let's go ahead and look at, I'm going to write on the board today. We'll see how this goes. I think it might be a little too much for the pad. All right, so get your notes out, and of course that means I'm going to be farther away from the microphone, so I'll have to talk loud. All right. See if that
I think we
makes
should take a second and move all the desks a little closer to the front. Because they keep like switching backwards.
I usually do that in the morning, and I forgot.
I think we should.
You can move yours
No,
It would feel weird.
I wouldn't feel weird.
All right.
I think you should use
How's
the
that doing?
board
Is it working?
thing so much more because it's so cool.
So fun. I don't know. Some people would bother because they don't know where to look. They're here, then they're there. You're all confused. All right.
Hello.
Come take your math test? The answer is no.
But he's in that class.
Okay. You want to look like the president of the world?
Yes.
You just follow the rules. Right?
I'm
You do
just
what you're
following the rules.
doing your job. Maybe you better go.
It would not be fair to send a message to your morning teachers that their class is not important.
Yeah.
We want the math scores to come up, so since you've just had a refresher in math, really
Yes,
well.
Yeah.
Hopefully there's some solids of revolution.
No.
What if there are though?
There are not.
What if we start? Have you taken it yet?
Can't believe that.
Last year, it didn't really go past. Well, I guess there was some, but not.
Yeah, there was a.
Special line. Hang around, Miss Aguilar. Cool stuff. Yeah, it's too hard to miss. That
That's
is the
nothing
problem.
to do with it.
A couple people did this as well.
Where are the scholarships?
All right, yes, we are. Those of you that have been in physics,
Oh, for real? Oh, yeah.
Yeah, we're gonna-
I remember
we're
this.
talking about work. So if you have been in physics, now the other class, we decided that those people that have been in physics were on equal footing because they didn't remember anything.
No,
You know,
because it's not work if you don't go.
It's, right? So what is the formula in physics for work?
Oh. Force
Force times distance. It's actually displacement. It actually is displacement. But if I mean, that's it. It's force times distance. So the force is measured, depends what units. If you're talking English units, the force is in pounds typically, and units, let's say feet. So a common work unit is foot-pounds. Remember we talked about kilowatt hours, right? Those kind of things. It's not uncommon to have units where it's 2 units multiplied together. And so a unit of work is foot-pounds. If you're using metric units, it's usually the force is newtons and meters for distance, so Newton meters is used. Now, that's also the more commonly referred as joules, right? A joule, Joules, joules. 1 Newton meter is 1 joule of work. Now, like I said, it's not work if you don't move. If I stood here and held a really heavy object over my head, you know, and pretty soon the arms start shivering and, you know, shaking and whatever, and it feels like you're really doing something, but you're not doing work. If it's not moving, you're not doing work. Now, if you lift something over your head, so if I took a 5-pound book and lifted it up 6 feet, right, from where I started to where it ended up, that's 30 foot-pounds of work. 5 pounds times 6 feet, 30 foot-pounds of work. That's the units. Okay, now, when you're in a high school physics class, you always are dealing with a constant force. Much like we talked about distance and velocity and acceleration. In physics class, you're usually, almost always, all the formulas you have a constant acceleration. So you can do things with average velocity and things like that. In calculus, then, we talk about what if it's a variable acceleration, and we can deal with those changing quantities. Well, we can do the same thing here. So when you get into college and you take a calculus-based physics, then you take those same principles, but you apply them with changing forces and changing accelerations, because acceleration is really a force as well. So the biggest difference between a high school physics and a calculus-based physics is you deal with changing forces. Okay? And so that's how we're going to deal with it. So technically, and I don't know if Mr. Euler or Mr. Mandernack, those guys talk about it, but if you take a 5-pound book and you lift it from here up to here, the book may weigh 5 pounds here, but it weighs less when it's up here. Why is that?
Because it's further away.
Further away from the center of the earth, right? The weight of the objects depend on gravity, and that's dependent on how far you are from the center of the earth. Now, from here to here is a pretty small difference, and it would be, how many, decimal places out there, who knows, right? We're going to ignore that. We will ignore that, just like in physics, I say they would ignore that distance or that change. Okay? So we'll keep it relatively simple. And this is going into a Calc 2 topic that, once you get to college Calc 2, you would get into this in more depth and more detail than we're going to do. We're going to keep it fairly simple. We're going to do 3 types of problems today, and we're going to, on the test, you have to do 2 of them. The third one we'll talk about maybe would be a bonus, if anything, but it'll be in your homework at least one time. I do want you to see. Okay? All right, so the first one, so we're talking about foot-pounds, Newton meters, those would be our units, okay? We'll deal mostly in the English one, so foot-pounds will be our common. All right, so the first type we're going to do is going to be the spring problem. We're going to have 3 different types of problems. So the first type of problem we're going to have is going to be the spring problem. Now, what we're going, the basic idea here is that we're going to use the integral to add up the amount of work through the distance. In other words, if we're going to have a variable force, and let's use the book example again. If the book weighs less up here than it did down here, even though that in that example we're going to ignore it, okay? But we'll have similar examples. Then the calculus idea is, okay, well, how much work is done for maybe a movement of 6 inches? Right? Because over a 6-inch span, the force is relatively constant. Right? Isn't that the same thing we've done all the time? Right? Think about the lemon. We sliced it into 6. Well, the lemon changed, those slices changed shape. But what if we did 10 slices or 100 slices, right? Then all of a sudden, each of those is more consistent and becomes a cylinder, and then we said, but they get infinitely small amount this way. Okay, as far as thinner and thinner and thinner. We're going to do the same thing. So if the force is changing through the whole 6 feet, what if we did it in half-foot segments or 1/3 of a foot or whatever? And then we use the integral to calculate or to add up all of those segments or slices, if you want, of work all the way up. That's what we're going to do. All right? So what we want to set up is we want to set up some sort of integral that's got pounds times feet or feet times pounds in it. And that's going to be what we're going to want to do in all of these examples. Well, for a spring, it's going to look like this. Our force, which is measured in pounds, and the dx is going to be the feet, because in my example, like I said, we do a 1/2 foot, or 1/3 of a foot, or 1/8 of a foot, or whatever. The distance is going to get smaller and smaller and smaller, and we're going to calculate the force required for those small distances, and then we're going to add all those up. But we're going to get force times distance, but the dx will turn into be the distance. Okay? All right. Now, for a spring problem, the force equation is going to be Hooke's law. Okay? Now, when I talk about a spring, we're talking about like a metal coiled spring, and we're talking about stretching it or compressing it, and the force that's required. Because as you stretch it, it gets harder and harder and harder and harder to stretch it. So the force is changing, okay, as you go through. And it is proportional to how far you stretched it. So the bigger X is, the bigger K is. Okay, the farther you've done that, the more you've stretched it, the bigger K is for that force. Okay? K is called the spring constant. Big, thick spring is going to be harder to pull. Smaller spring would have a smaller K value. Okay? All right, so the problem is going to be kind of like this. Well, let's see. I've got I had a PowerPoint, but it doesn't work good when I do the video. So here's going to be the problem. A 1 meter spring. Oh, let's do a 1 foot spring. Yeah, I keep changing my units here. A 1 foot spring. Now, we don't want to complicate it by stretching from both ends. So we're going to say the spring is just attached to the floor, or it's attached here to the wall, and we're going to stretch it. Okay, just one direction. Okay, so it's anchored on one end, and we're going to stretch it from one. So we have a 1 foot spring. That's called its natural length. So there's no force being exerted, just at rest. Here's the spring. We're going to stretch it to 1.8 feet, and that requires 24 pounds of force. How much work to stretch to 4 feet? Okay, so that first piece of information is important because it tells us something about the spring. So anybody have an idea what we would do from here? No, we could. We could set up the A and B, but let's leave that for a minute. Logan. This right here. So what would I put in for F? 24 pounds. Force is pounds, so F in this case is the force. That's pounds. No. 0.8. Right? So X in this case is the stretch distance. The stretch distance, not the spring length. It's the stretch distance, okay? So 1 foot spring, and we're going to stretch it to 1.8 feet. Notice, okay, I said it, but I didn't write it. Okay, that would be confusing. Let me add that word in there. We're going to stretch it to 1.8 feet, right? The way I wrote it, it just says we're going to stretch it 1.8 feet. So you see what I mean? So that could be confusing. So you do have to pay attention to how it's worded. Are you stretching it 1.8 feet, or are you stretching it to 1.8 feet, right? Because it's starting at 1 foot, right? This is what I meant. We're going to stretch it to 1.8 feet. So our stretch distance was 0.8. So we divide that, we get K equals 30. So for this spring, our K is 30. So our force equation is 30x. So that goes into the inner. Okay? Our force equation is 30x. And now, Spencer, like you were saying, from where to where? Remember, x is the stretch distance. How much work to stretch to 4 feet? Now, what we meant is from its natural, not from the 1.8. Okay, that's just from its natural length. And again, if this was a problem, it'd be worded better. I was trying to shortcut it as I wrote this. The question would be, how much work is required to stretch the spring from its natural length to 4 feet? No. 0 to 3. Because from its natural length, what's the stretch distance? 0. And to go to 4 feet, you've stretched it 3. It was a length of 4, or length of 1, and you stretched it to a length of 4. So you stretched it 3 feet. It's always at stretch distance. How much has it been stretched? Okay, so it started out at 1 foot, so it hasn't been stretched at all, and it ended up at 4 feet, which is a stretch of 3. So it went from 0 to 3. So if you did the integral from 1 to 4, what would you be finding? Stretching from 2 feet of length to 5 feet of length, right? Because 2 feet would be a stretch of 1 to a stretch of 4, because 5 feet would be a stretch of 4, because its natural length is 1, right? So 1 to 4 would be a bigger number, because it would take more work to do that, right? It would be harder, right? It would be harder, because the farther you stretch it, the harder it gets to stretch it. All right, what'd you get on this one? Anybody got it? 135 foot pounds. 135 foot pounds. Okay? That's it. I mean, that's all that really is involved in the spring type equation. That Hooke's law, finding what K is, which gives you your force equation. Notice, again, this is pounds in here. This is feet right here. That's why our final answer is foot-pounds. The dx is the feet. We're going to pull it a little bit, and a little bit, and a little bit, and a little bit, a little bit, and then add all that up. Because the force is changing, right? And so this is the equation that gives us that force change. All right, next one. All right, so that's the first type of problem, is the spring. Second type of problem is the bucket. Okay? Bucket problem. We're going to pull the bucket up out of a well or pull it up a distance. Okay, we've got a pulley here, and it's right, and a rope attached, and we're going to pull this. It wouldn't have to be a pulley, but we could a rope attached. Okay, and we're going to pull this up. Now, we're going to call this 0 down here, and we'll call this 20 feet up here. So we're going to pull it the distance. Think of that as your y-axis if you want. Okay? And so 0 starts down, and we go upward like we would. Okay? And we want to pull this up and over the top. So 20, well, I didn't do that very good. The 20 should probably be up here. Okay? Oops. I need to use my fancy eraser. Okay, so the 20 would be up there. Now, there are a couple things we can do in the bucket problem. Okay? We can just do a basic bucket problem. We got a bucket filled with water, and we're going to pull this up. Now, we're going to ignore the fact, again, that the bucket actually weighs less when it gets up here than it did down there. The whole gravity in the center of the earth thing. We're going to ignore that. It's a very, very tiny one. But what we're not going to ignore, which you would ignore in physics, we're not going to ignore the rope. Because when you first make that first pull, you're not only lifting the bucket, but you're lifting 20 feet of rope. But when the bucket's halfway up, now you're only lifting the bucket and 10 feet of rope. Right? So the force required gets less as you pull it up because you're pulling up less and less rope. You're lifting less rope. Okay, and that's the part that's ever changing. Now we're going to say we're going to do this at kind of a constant rate. All right? So we're not going to ignore that part of it. All right? So when we set up our integral, now there's no formula like there was with Hooke's law. It's simply we're going to want to do pounds and then feet. We want to set up an integral where we add up the pounds and the dx will be the feet. Because as we pull it, as we pull it this far, the rope has changed throughout that whole thing. So we'll just take little slices of work, and add those up as we go along. Okay, so what are the different forces? Well, we have the bucket. Okay, and we have the water. So we're just going to build our formula. And we have the rope. Okay, so we need the pounds of all of those things added together. Okay, And then the dx will give us the feet. So that'll be the dx over here. All right? Now, let's say it's a 5-pound bucket. Okay? And let's say there is 15 pounds of water in the bucket. So we could have added that together and just called it 20 pounds. Now, in physics class, you would just say, and we're going to do that, what, 20 feet? So in physics class, you would just say, okay, we're going to have 20 pounds. We're going to lift it 20 feet. That would be 400 foot-pounds, right? 400 foot-pounds. And we would ignore the rope. Okay? Or we would just see how much 20 foot weighs, and we would just do that. Okay? But we're going to figure this in. All right, anybody have an idea of how I would write the rope? Now, I got to do this in terms of x, the distance. And I'm going to tell you that the rope weighs 0.08 pounds per foot. That's what the rope weighs. The rope weighs 0.08 pounds per foot. That's how you're usually given that number. Ideas? Let's think about this. 20 times 0.08, because that's how much rope you'd have at the beginning, right? 20 feet of rope times 0.08 pounds per foot minus 0.08 x. Because you're losing, as you pull up the rope, you're losing 0.08 pounds every foot, and x is the number of feet that you've pulled it up. Right? Because you're losing rope. You have less rope. I would agree with that. Because x, remember, is how much rope is out. So at 0 feet, how much rope is there? There's 20 feet of rope. When you've pulled the bucket up, yeah, x is how far you've pulled up the bucket. So at 0 is at the beginning, right? Now, yes, there's several ways we could have written this. We could have also written it as 0.08 times 20 minus x. Now think about that. What does 20 minus x represent? This goes back to what Keith was just saying, but he just had it backwards. 20 minus x represents how much rope is out, right? If 0, it means all the rope is out. So basically what this is saying is it's 0.08 pounds per foot times how much rope is out. Well, it's 20 minus x. At the beginning, there's 20 feet, and at the end, there's 0 feet. So it's 20 minus x is how much rope is out. So we could have just started with that. Here's another way I like to think of these, is do it as an ordered pair. It's just a linear equation. Think of feet and pounds as your ordered pair. Now I'm going to tell you why, because we're going to get to the water here in a second. So 0 feet out, you've got 1.6 pounds of rope, right? That's 0.08 times 20. So with 0 feet of rope pulled up, you've got 1.6 pounds of rope. At 20 feet, you've got 0 pounds of rope left, right? And just think of it as an ordered pair, and just do a slope calculation. So 1.6 minus 0, 0 minus 20, you get 1.6 over negative 20, which is, guess what, negative 0.08, right? Now just write that as an equation. It's your slope, so y equals mx plus b, plus your starting point, and that's the same thing. See how that's the same thing as that right there? Okay, so it's just, we're going to lose 0.08 pounds every foot, that's why it's negative, plus our starting point, our y-intercept, if you will, your starting point of 1.6 pounds. Any of those three are legitimate things to put in. So whichever one makes more sense to you, you know, is fine. If you like the 0.08 times 20 minus x, or you like this one, or whatever. Okay? So there you go. Now the integral is going to go from what to what? Think of it like slicing. We're going to take a slice of work, a slice of work, a slice of work, a slice of work, and that's going to be from 0 up to 20 that we're adding up. Remember, it has to match here. dx is feet. Oops, So that's 0 to 20. And that's what we would do. All right, now I'm going to add something into this. There you go. There's a hole in the bucket. It's a leaky bucket. It's a leaky bucket. There is 15 pounds in the bucket. There's 15 pounds of water at the beginning, and it's empty when you get it up to the top. Yeah, but you didn't know that, right? You pulled it up, and you're like, how does it get wet? No, there's nothing left, right? It's a leaky bucket. So that's another way we can bring in a variable force. Okay? So the leaky bucket problem, what's going to change up here? To 15. Okay? But we can approach it the same way as we did this. Right? We're going to say we're losing water at a constant rate. So at what rate are we losing the water? If it's empty, we'll make it easy. It was empty by the time we got up there. So you lost 15 pounds in 20 feet. So 15 20ths, 3/4. So we can take 3/4 times 20 minus x again. Right? So it's the same principle as the row. Or we could think of it as, okay, we started with 0 at 0 feet of rope, we had 15 pounds of water. At 20 feet of rope, we had 0 pounds of water. So that's negative 15 20ths or negative 3/4. That's our slope because we're losing that. And then we could have said, all right, that's negative 3/4 x plus how much we started with at the beginning, which is how many pounds, right? It's always pounds. How many pounds, which is 15. Well, that's the same thing if you do that right there. Okay? So, the weight of the water, again, if you like doing it that way, was that right there. All right? So, it was filled with acid instead of water, which was eating away at the bucket. And, and the rope was on fire, and so as it was coming up, it was burning in. Okay. All right, which of course was creating carbon, which was adding to it. Okay, so like I said, we're going to keep it simple, but yes, we could complicate things if we wanted to. All right, so that's number 2. That's number 2. But notice how we built the integral. Foot-pounds is going to be our answer. Now the dx was feet, and all we were doing was writing the pounds of the various elements in the problem. Okay, and so we have that. So and we won't get much more complex than that right there. All right. Now.
That's such a cute little note.
Yeah, I kind of like that. The last one is going to be pumping liquid, kind of a problem. So, we're going to start with a tank of liquid, a cylinder-shaped tank of liquid, and
Is it on a hill? It's on a hill.
it's yeah. Well, I would think you'd be used to that. Yes,
We still like to make fun of it.
horizontal on the bottom, just the way it looks. Oh, it even looks. Does it look worse over there?
Yeah.
It almost looks worse over there. All right. Oh, that is bad. Okay. If you get like right here, no, it's still bad.
If you
All right.
squint at it and
Is it-
tilt your
it's
head and
So
turn around.
now, what we're going to do. So this is a distance of 10. Okay. This is 4. This is going to be 10 across here. Okay, this will all be in feet. Now think of this like a gas station, right? This is exactly what this would be. All right, you've got a tank buried under the ground where the big gas truck comes and fills up the tank there. And then above ground, you have your pump. And so there's a motor attached that is pumping this up out of the tank to the top. How much work, how much horsepower is needed, how much work is involved? Well, Now, this one we're going to think of a little differently. Now, so it's different than the last two. The last two, we just wrote our integral, and all we wanted was a pounds equation, and then the dx was the feet, and then that gave us foot-pounds. This one's going to be a little different. But it is actually more like the things we've been doing with slices and that sort of thing. So from that standpoint, it's not too bad. So, as we look at this, here's how we're going to think about this. And this is how it's a little different than the last two problems, but a little more like what we've done before. We're going to think of a strip across here. Now, what that strip represents, actually, is a slab, a disc of liquid. If this is gasoline, let's say. I think in the example in the book, it's water. Okay? So, think of a cylinder-shaped slab of water. However, we are going to want that to become an infinitely thin slab of water. So that's the dy actually right there. So it's going to come in a different way than the dy or the dx came in the last problem. Okay? Now, this is 0 down here. This would be 14 up here. Okay? So we're still going to think of this strip. We're going to label that as a y. Right? Now, I don't want you to confuse the y and the dy. I just want you to understand the width of that is going to be the dy, like it is on any horizontal strip that we do. Okay? But we're going to label it as y there because how high off the ground is that slab? Well, it's y units, right? If we think of the y-axis here. So 0's down here. And so the slab is there because slabs that are down here have to get pumped farther than ones that are here. Now remember, it was displacement, right? So in the calculation of work, if a slab of liquid goes down to here and then gets pumped back up to here, this part going down and this part going up cancel each other out, right? Because it was force times displacement, all right, in the calculation of work. All right, now, so ones that are up here, the work calculation is how much work it took to take it from here up to there. All right. So now as we build this, we have to think of what is the weight of this slab of water. What is the pounds that we are lifting? Okay, the pounds is the weight of the liquid. Well, what do you need to calculate the weight of liquid? Come on, chemistry, science people. Volume and density, right? Density is pounds per cubic foot, and then times the volume, which would be the cubic feet. So we need density. So the weight of the liquid is the density times the volume. Okay? Now, you'll be given the density in the problem. So in this particular problem, we're going to say it's water, and I think in your homework tonight, it's 62.4. They say it's 62.4 pounds per cubic foot. Okay? So 62.4 pounds per cubic foot would be 1 unit of density. And then when we take that times volume, you can see how that's going to give us pounds. Okay? So the density of the water is 62.4 pounds per cubic foot times, now we need the volume of that slab. Well, what shape is that slab? It's a cylinder, which is pi r squared h. Now, you could have all kinds of different slabs because you could have different shaped tanks. We won't get into all that. The only kind I would ask you would be something fairly simple like this. Okay? So it's a cylinder-shaped slab of water, so the volume would be pi r squared h. Well, so pi is just constant. What is the r in that one? And it would always be 5. Every slab would have a radius of 5. And then what's the h? The dy. See, that's where the dy is going to come in this problem. Because they're going to be ever thinner slabs that we would be thinking about adding up. All right? And the integral is going to add up all the slabs. Now, what are we missing here? We need feet. Yeah, we need a y in there, you would think, right? It wouldn't always be just a constant. Because remember, we want to have our integral end up being foot-pounds. Now, in the last, this is why I said it's different from the last two examples. The last two examples, the dx was the feet. Not in this example. The dy, the dy is in feet, but it's part of the cubic feet right here, right? So those canceled, and now all we have right now is pounds. So we need something that's feet. In other words, how far is that slab going to move? How far is this slab got to move? Remember, we ignored this back up to here because of the displacement. So how far does that slab have to move? 14 minus y. It's just like finding p, right? It's just like finding p. It's got to move from here to there. 14 minus y is how far it has to move. And so that is that. So again, when we write that, type in the calculator, of course, the dy would get shoved out to the right-hand edge. Now, we're not quite done because we got to put the limits on the integral. From what to what? Here's where you think about just like we've been doing it. The strips fill the space from 0 to 10. Because the water is only from 0 to 10. This is like empty space here, right? The tank was full, by the way, right? If the tank only was 8 foot full, then you would just go 0 to 8, right? Then you just go 0 to 8. So the strips of the slabs, the strips of water would fill the space from 0 up to 10, and there it would be. So a little more complicated, but a few people in their class thought that was almost easier even. Now, there is one other way we could complicate this. Remember I said we could have different shaped tanks, so different shaped slabs. In keeping with a cylinder slab, and I wouldn't even worry about writing this one down, to be honest with you. But here's another problem that was in the PowerPoint. What if the tank was this? And it was filled, let's say to here. Let's say this was 0. This is 10. Let's say this was 2 right here. Okay, which means this would be 8. Okay? The example in the PowerPoint's kind of funny. It says you got a 10-foot conical shaped tank of salad oil. Trying to imagine this 10-foot tank filled with salad oil. But it said how much work is required to pump the liquid up out of the tank and over the edge. Okay? So it would be very much the same. Here would be our one slab, our strip, if you will. Okay, that we're going to pump. Now, what would change over there? Well, since it's salad oil, the density would change, right? What else would change? The volume would change. I think in the example it was 57 pounds per cubic foot. It's still a cylinder-shaped slab, so it's still pi, but now the radius is not going to be a constant 5 all the time. So we're going to have to deal with that. We'll come back to that. The dy would still be that. So there's our pi r squared h. And then instead of 14 minus y, this one would be 10 minus y, because we're going to pump it up over the edge of the tank. So here would be the strip y. Here's where it's going to pump to. So it would have to go a distance of 10 minus y. But the integral would only go from 0 to 8, because the strips, the slabs would fill the space from 0 to 8. What would be this radius? Well, what you would have to do in a problem like this is you would have to put in like an xy axis, because you're going to need an equation for this line. You're going to need this, because wouldn't the radius be that right there? Wouldn't that be the radius of the slab? It would be the right x minus the left x. It'd just be a right minus left. Well, what we need is this equation. Well, since this is 10 up here, and I didn't even tell you what this is across here. Let's say the radius up here is 5. What would be this slope? Well, it'd be up 10 over 5 would be 2. If we make this the origin right here, it'd be the line y equals 2x, right? To make it easy, we'll just put the tank right there at the origin. So that would be x equals 1/2 y, correct? So the radius would simply be this x coordinate, which is 1/2 y, minus this x coordinate, which is 0. So right here you would have 1/2 y as your radius. So you could get a situation where the slabs had a different radius. And I'm not going to do that to you. I think you have an example in the homework that's like that one. But that's where that could change. But that's it. That's a pumping liquid, the work required to do that. And I know that's a popular topic in Calc 2 applications, you know. When you get, this is not on the findings.
None of it?
None of the work is. Darn it. I mean, if you think about it, we've been through all these packets and we haven't seen it, right? You haven't seen that. But I do think it's a nice, I like it. I like it as an application. We'll just keep it pretty basic. These 3 examples I just showed you is all that you would have to do. And on the quiz, the pumping liquid one would probably just be bonus, if anything. All right, so let's look at the homework then. You're going to do this is in your book now, I believe. I think it's on the assignment sheet, but I'll just write it. Excuse me, I'll write it down here for you. So this is on page 437. It's section 7.3 in our book. 1, which is a spring problem. 5 is a bucket problem, but I think it's an elevator being lifted, and it's elevator in the cable. Okay, same exact as a bucket problem. 6 is a pumping liquid problem, like this first one we did. 7 is another bucket problem. I think it's a comparing one bucket versus another bucket, which one is more work. And then 12 is the last one, and that's a leaky bucket. That's a leaky bucket. So so those are the problems. Now again, I gave you some of those other volume ones. You could go back and do, although it might not be a bad idea. I think I do have a review worksheet later on with some volume ones and some area. It doesn't review the work ones necessarily. We can come back and talk about some of those. But the quiz is probably going to be early part of next week. Tomorrow we'll go through and see if you've got any questions on these. We'll probably do some more work in the sample packet. I'll probably give you another thing of worksheets at some point along the way, or some problems this week. And then we'll be quizzing like crazy.
I have a quick question.
Yes.
Can I answer it?
Yes.
I get